So today we're going to be looking at section 5.2, which looks at the characteristic equation for a matrix A. This is going to be an equation that we can use to find the eigenvectors and eigenvalues of a matrix. So to start out, I want to look at what this characteristic equation actually looks like. So we already know that we have the equation A times x is equal to lambda x. In this case, lambda would be the eigenvalue of A, and the x that went with lambda would be the eigenvector. Remember, x cannot be the zero vector. We never count the zero vector as an eigenvector. So if this is the case, then we said that we can rearrange this. Bring the lambda x onto the left-hand side and make it equal 0. And then we talked about how we can factor out that x vector so that we would get the equation a minus lambda I times x is equal to 0. And remember, we have to take out lambda times I because we can't do a minus lambda. A is an n by n matrix. It's a square matrix. Lambda is just a value. So in order to make sure that I can do a minus some value, okay, it has to be a matrix of the same dimension. Otherwise, it does not work. So we do lambda times the identity, which will give me a scalar multiple of the identity, and that makes more sense to subtract, okay? But these two things are equal to one another. All I've done is rearrange. So we've got down to this equation here, and we know that this is satisfied for any lambda that is an eigenvalue and a non-zero x, which is the associated eigenvector for the eigenvalue lambda, okay? So because of that, by the invertible matrix theorem, okay, if you treat this as some matrix B, what you've effectively got is B times x is equal to 0, okay? X is not allowed to be the zero vector, okay? We want to have a non-zero vector x for this thing to be an eigenvector of A, okay? So because we don't want x equal to 0, we want some other non-trivial solution to this equation. We have to make sure that therefore by the invertible matrix theorem that B would not be invertible. So because we want a non-trivial solution x, or a non-zero solution, by the invertible matrix theorem, okay, I'll just write that as IMT. By the invertible matrix theorem, we know that this B, okay, if x is non-trivial, okay, and we have a non-trivial solution to this homogeneous system, that means by the invertible matrix theorem, this thing cannot be invertible, okay? It's only invertible if the only solution is x is equal to 0. But x is equal to 0 is not an eigenvector, so if x is an eigenvector, it must mean that we can find a non-zero solution to this thing, and therefore B, or A minus lambda I, cannot be invertible. Okay, so if lambda is an eigenvalue with associated eigenvector x, which is not the zero vector, that must mean that A minus lambda I is not an invertible matrix. So because it is not invertible, think back to our invertible matrix theorem, that must mean that the determinant of that matrix is 0, okay? If it's not invertible, that means it's a singular matrix. Any non-invertible matrix has a determinant equal to 0. If the determinant is non-zero, it means it's invertible. So we know that the determinant of A minus lambda I has to equal 0, okay? So this thing here, the determinant of A minus lambda I equal to 0, this is called the characteristic equation for the matrix A. Now, what does this thing look like? Well, when we do A minus lambda I, okay, as I've mentioned before, when you subtract lambda I from a matrix A, what it's going to do is it's going to subtract that eigenvalue lambda off of every single entry in the diagonal of A. Okay, so it's going to subtract lambda from every diagonal entry in A. Therefore, when we actually go ahead and solve this thing, so we find the determinant of A minus lambda I, and we set that equal to 0. When A is an n by n matrix, and therefore we use the n by n identity. So A is an n by n matrix. What you should get when you solve this determinant is a polynomial that has degree n. Okay, so for an n by n matrix A, you should get a polynomial that is in lambda that has degree n. So where A is an n by n matrix, the characteristic equation, and we will do some examples of this where you can see this in action. The characteristic equation of A is just a polynomial in lambda of degree n. Okay, so for example, if you had a 2 by 2 matrix A and you wanted to find its characteristic equation, when you get that characteristic equation, you're going to try and solve the characteristic equation for lambda. When you solve the characteristic equation, those lambdas are the eigenvalues of A. Okay, because we know that lambda has to satisfy this equation. Okay, so whatever lambda satisfy that equation must satisfy this polynomial, and therefore they are the eigenvalues of A. So let's go ahead and do an example of this because it's way easier to see it once you've actually seen an example. Let's find the eigenvalues of A equal to 2772. Okay, we're just going to do a 2 by 2. What we should get out of this is a quadratic equation in terms of lambda, because we've got a 2 by 2 matrix. Therefore, we must get a degree 2 polynomial in lambda when we get our characteristic equation, and we can solve that to get 2 eigenvalues. Okay, keep that in mind and keep that theory in mind for a second, because we're going to be doing something slightly different in a second. But let's go ahead and solve this right now. So we want to solve the determinant of A minus lambda I equal to 0. Okay, I'm going to find this thing and then solve for lambda, and they will be my eigenvalues. So A minus lambda I, let's start there. A minus lambda I is A minus lambda times the 2 by 2 identity is that, which gives me 2 minus lambda, 7, 7, 2 minus lambda. Now I can get the determinant of A minus lambda I and set that equal to 0. So the determinant of this matrix, the determinant of a 2 by 2 is this entry times this entry minus this entry times this entry. So it's AD minus BC, okay? If you look back at your notes. So that should give us 2 minus lambda times 2 minus lambda minus 49 equal to 0. So what you need to do at this point is multiply everything out, okay? So from here, if we distribute this, I'm going to get lambda squared minus 2 lambda minus another 2 lambda, which will give me negative 4 lambda, plus 4 minus 49 equal to 0, okay? Now, if I simplify this, I should get lambda squared minus 4 lambda minus 45. So lambda squared minus 4 lambda minus 45 equal to 0, okay? Now I need two numbers that are going to add to -4 and multiply to -45, which would be -9 and +5. So I'm going to get lambda minus 9, lambda plus 5 equal to 0. So by solving this, my two options are lambda equal to 9 by setting this thing equal to 0, or set this thing equal to 0 to get lambda is equal to -5. So I have my two solutions to my characteristic equation. Therefore, these two are my eigenvalues. So lambda is equal to 9 is one eigenvalue of A. Lambda is equal to -5 is another eigenvalue. Okay. Now, at this point, you can go ahead and find the eigenvectors. I haven't done this in the notes, but I will show you quickly how to do this so that you are aware of how it all works. What you need to do is to substitute each of these back into this formula. So once you've got to here, you've got your eigenvalues. I'm just going to take it a step further to find the eigenvectors associated with each eigenvalue. Okay. Whenever it asks you this, okay, you need to find the eigenvalues first, okay? Whenever you do one of these problems, always find the eigenvalues first, then find the eigenvectors for each eigenvalue, but always find the eigenvalues first. Then, once you have done that, you're going to need this formula, okay? So, we haven't gone to the characteristic equation part of this, okay, because that doesn't help us solve for an eigenvector x. But we need this form of our eigenvector eigenvalue equation, okay? So always take it down to this form. And at this point, what you need to do is substitute in each lambda. So let's start with lambda is equal to 9, okay? Coming back to here, if I did a minus 9i, come back to here, a minus 9i, if we take it from here, substitute in lambda is equal to 9. That would give me -7, 7, 7, -7. So I'm going to get -7, 7, 7, -7 multiplied by this x. Now, I know that x has to be a two-dimensional vector, okay? I can't have a one-dimensional or a three-dimensional or any other dimensional vector multiply a 2 by 2 matrix. I know that I have to have a two-dimensional vector equal to my two-dimensional 0 vector, okay? The task now is to find x1 and x2. Now, you should find that there are infinitely many eigenvectors for each eigenvalue, okay? You should be able to take any multiple of a certain eigenvector, and that would also be another eigenvector of A. If you do not get that, you've probably done something wrong in your calculation somewhere. But you should get something that looks like this, okay? Now, all you have to do at this point, you can see that the second row is a multiple of the first row, okay? So if you were to row reduce this thing, okay, you would get 1, -1, 0, 0. x2 is a free variable. That already tells us we have infinitely many solutions. So what you actually get from this, once you've reduced it down, you should get 1, -1, 0, 0 as your augmented matrix. So solving for x1, x2, you put A with the 0 vector reduced down, and this is what you should get. So standard, like reducing an augmented matrix for a system, that's where you get to, okay? That therefore tells us that x1 minus x2 is 0. That means x1 is equal to x2, okay? You can see that from the top line. I'd get x1 minus x2 is equal to 0, okay? So x1 is equal to x2. Now you could set x1 and x2 equal to anything that you like at this point. They are equal and x2 is a free variable. So if x2 is a free variable, set it equal to whatever you like, and x1 will equal the same thing as x2, okay? So a particular eigenvector I'll call it an E vector, a particular eigenvector for A associated with lambda is equal to 9 is let x2 equal 1, therefore x1 must equal 1 because they are equal, okay? Now, this thing forms a basis for our eigenspace, okay? So this thing is a basis for our eigenspace, so the eigenspace of A associated with lambda is equal to 9 has basis. Okay, I take any multiple of that vector, it's also an eigenvector. Any multiple of this is also going to satisfy this equation. Okay, so 1, 1, 2, 2, 3, 3, whatever you want will satisfy this equation where lambda is equal to 9. Now let's do the same thing where lambda is equal to -5. Okay, let's go back to our matrix that we have. Back one more, here we go. So if lambda is equal to -5, that means from this matrix here, I'm going to get 7, 7, 7, and 7. So I'm going to get a matrix of 7s. So from doing A minus lambda I x is equal to 0, I get 7, 7, 7, 7, x1, x2 is 0, 0. Again, you should find that you should get infinitely many x vectors such that this is satisfied. Now that is the case because when you make an augmented matrix for this system and reduce it down, what you should get is this. Therefore, x2 is a free variable. So from this augmented matrix, we get x1 plus x2 is 0, and therefore this time we get x1 is negative x2. So x2 is free, and x1 is just negative of whatever you set x2 to be. So a particular eigenvector associated with lambda is equal to -5 is, so again, if I set x2 equal to 1, x1 is negative x2, so that would be a particular eigenvector. Again, if we wanted the eigenspace of A associated with lambda is equal to -5, it has a basis of -1, 1. So again, I could take any multiple of this vector and it would still be an eigenvector for the matrix A with eigenvalue lambda is equal to -5. So any multiple of that vector will satisfy this equation, okay? And therefore it's an eigenvector for A. Okay. So what have we learned from this example? Well, we started out with a 2 by 2 matrix A. From that 2 by 2 matrix, we then created the characteristic equation for that matrix, which was the determinant of A minus lambda I is equal to 0. Any eigenvalue lambda that satisfied that characteristic equation must be an eigenvalue for A. Now, we started out with an n by n matrix A. The characteristic equation for A had degree 2, okay, because we started out with a 2 by 2 matrix, so an n by n. So that gave us a degree 2 polynomial, okay? So if you start out with an n by n matrix, you should get a degree n polynomial for your characteristic equation. Any degree n polynomial has n solutions to it. So for our degree 2 polynomial, we had 2 solutions, 2 eigenvalues. So you should find for an n by n matrix A, it has n eigenvalues. Now, the issue that you have is that they may not all be distinct. So you may get a case where you have repeated eigenvalues, okay? And we will get to that a little later. But first, what I want to do is very quickly go through a 3x3 example. This is a very simple 3x3 example. I'm not going to expect you to do like some crazy 3x3 example because, of course, that would mean solving a cubic. So if you come back to what we had here, we were solving a quadratic. We know how to solve quadratics. Solving cubics is slightly more difficult. So I won't be giving you some crazy cubic to try and solve halfway through an exam. Okay, so this is kind of the level that we'll be looking at. So this example is find the eigenvalues of A equal to -1, 0, 1, -3, 4, 1, 0, 0, 2. Okay. So again, we need to find A minus lambda I, then we're going to take the determinant of that matrix and let that equal 0. So A minus lambda I, if you do this, it turns out that you just subtract lambda off of the diagonal entries. And now I want to take the determinant of A minus lambda I and set that equal to 0. Now, if you look at our matrix here, okay, using the cofactor method where normally we go across the top, we take, if you remember our pattern that we use for taking a determinant of a 3x3 or higher dimensional matrix, okay, we tend to do positive of the first entry times the determinant of the 2x2 matrix that we get when we delete that row and that column, minus the second entry times the 2x2 determinant that we would get if we deleted that row and column, and then plus the third entry times the determinant of the 2x2 matrix that we get by deleting its row and column. Okay. Now, if we do that, looking at this matrix, on the bottom row, because you can expand around any row or column that you like, but if we look at the bottom row, we have 0, 0, and 2 minus lambda. So if I use the cofactor method by expanding along the bottom row, all I get is positive 2 minus lambda multiplied by the determinant of this 2x2 matrix. So this would be the same as saying 2 minus lambda multiplied by the determinant. I'm going to use straight lines down as the matrix determinant just to signify that rather than writing determinant. Okay. So it's 2 minus lambda times the determinant of that 2x2 will equal 0. Now, taking the determinant of this 2x2, you do A times D minus B times C. Well, B times C is going to be 0. So this thing is going to become, let me write this out, 2 minus lambda multiplied by -1 minus lambda multiplied by 4 minus lambda. And then we would get minus 0 times -3. Well, that's just 0, so we don't have to worry about that. And that equals 0. So we get 2 minus lambda, -1 minus lambda, 4 minus lambda equals 0. So you don't have to like multiply anything out in this case like we did with the quadratics in order to then factor it again to solve it, okay? This thing comes already factored. I'm not going to give you some crazy cubic that you're going to have to try and solve, okay? It will be something like this where it's super easy to figure out what the solutions are. So in this case, your eigenvalues are lambda is equal to 2 if that was 0. Then if this was 0, you're going to get lambda is equal to -1. And if this was 0, you get lambda is equal to 4. So we have 3 eigenvalues. In this case, they are distinct eigenvalues. 3 eigenvalues where you had a 3x3 matrix. And therefore, your characteristic equation was a cubic. So it had degree 3. And therefore, you've got 3 eigenvalues. So what you should notice, as I said, For an n by n matrix A, the characteristic equation is a polynomial of degree n, and therefore we have n eigenvalues. But they may not all be distinct. So, for example, I'm going to do a diagonal matrix here. So let's find the eigenvalues for A is equal to 5, -2, 6, -1, 0, 3, -8, 0, and 0, 0, 5, 4, and 0, 0, 0, 1. Now, we talked about this in 5.1, but if you ever have a triangular matrix, whether that be upper or lower triangular, the eigenvalues of the matrix are just going to be the entries on the diagonal. So in this case, you have a 4 by 4 matrix. So if you were to go ahead and find its characteristic equation by doing the determinant of A minus lambda I is 0, if you want to go ahead and do that, feel free. What you would come out with is your eigenvalues being 5, 3, 5, and 1. Okay, the entries on the diagonal. So whenever you've got an upper or lower triangular matrix, the eigenvalues are just the entries on the diagonal. But lambda equals 5 occurs twice. Okay, so we have 4 eigenvalues, but they are not distinct. You only have 3 distinct eigenvalues, with one of them occurring twice. That is called a repeated eigenvalue. And the way that we actually write this is that we say that lambda equals 5 has a multiplicity of 2. Okay, so we say that lambda equals 5 has multiplicity 2. Because if you were to go ahead and find the characteristic equation for this matrix, you would actually get this formula. That would be your characteristic equation. So whatever the multiplicity of the root is in the characteristic equation is the multiplicity of that eigenvalue. So in this case, lambda equals 5, okay, have multiplicity 2, okay, because lambda minus 5 was squared in my characteristic equation. Therefore, we say that lambda equals 5 has multiplicity 2, okay. So it's almost like you have some amount of distinct eigenvalues, but some of them may occur more than once. The amount of times that they occur is their multiplicity. If you have n distinct eigenvalues, then that means that each one has a multiplicity of 1. But in this case, we would have a multiplicity of 2 for lambda is equal to 5. So it's just whatever the multiplicity of the root is in the characteristic equation. If this thing was cubed, then you'd say it had multiplicity 3. Okay. The other thing to be aware of, if you ever get a characteristic equation, let's say instead, assume you found a matrix A had characteristic equation. I'm going to make this up just to prove a point. Characteristic equation, let's say lambda times lambda minus 3 squared times lambda plus 1 is equal to 0. Let's say that that was your characteristic equation. Okay. Now you know that lambda equals 3. So 3 is going to be an eigenvalue of A, and it's going to have multiplicity 2. Then lambda is equal to -1. -1 is going to be an eigenvalue, it's just got multiplicity 1. Then you have lambda out the front. That means that 0 is an eigenvalue, okay? Because the only way, remember you have to set each of these things equal to 0. That must mean that lambda equals 0 is an eigenvalue. So if lambda is a root of the characteristic equation, that means lambda is equal to 0 is an eigenvalue of A. Now, if you remember back to right at the end of 5.1, we said that if lambda is equal to 0 is an eigenvalue of A, that means A cannot be invertible. The only time you have an invertible matrix is when you have just non-zero eigenvalues. So when that is the case, lambda is equal to 0 is an eigenvalue of A. That must mean A is not invertible. Okay. So, quick recap coming back to here, okay? Whenever you have an n by n matrix, it's going to have n eigenvalues. Some of them may not be distinct, but if you were to count their multiplicities, they're going to add to n, okay? So in this case, lambda is equal to 1 have multiplicity 1, lambda is equal to 3 have multiplicity 1, so you're up to 2, and then lambda is equal to 5 have multiplicity 2. That gives you 4, and you have a 4 by 4 matrix. So counting multiplicities, you have n eigenvalues for an n by n matrix. So that's always a good thing to check whenever you have your characteristic equation. Always check that that polynomial has n roots, but they may not all be distinct. Okay. This is a side note here. And will take us into something that we're going to talk about later on. It's a definition that I want to go through, and it's called similar matrices. So what does it mean for two matrices to be similar? Please, please, please do not confuse this with row equivalence. Okay, so we said, for example, when you've got an invertible matrix A, it's row equivalent to the identity because you can reduce A using Gauss-Jordan to get down to the identity matrix. That means that the two matrices are row equivalent because you can reduce one to get the other. Please don't confuse that with what we're going to talk about now, which is similar matrices. So A and B are said to be similar matrices if there exists an invertible matrix P such that A is equal to P, B, P inverse. So if I can find some invertible matrix P such that this is true, then A and B are said to be similar matrices. On the other hand, there's another way that you can rephrase this. If I were to multiply both sides on the left by P inverse, so if I multiply by P inverse here and P inverse here, and I multiply both sides on the right by P, so I multiply by P here and P here, what I end up with is B is equal to P inverse AP, okay? Both of these are saying exactly the same thing. So if I can find an invertible matrix P such that that is true, then we say that A and B are similar matrices. What I'm going to prove is if A and B are similar, then they have the same characteristic equation okay, so you're going to end up with the same degree n polynomial for both A and B when you found determinant of A minus lambda I is 0 and the determinant of B minus lambda I is 0. You're going to end up with the same polynomial, that same characteristic equation for both of them. So they have the same characteristic equation, and therefore if they've got the same characteristic equation, that means that they must have the same roots for the characteristic equation, okay? You've got the same equation twice, it doesn't change its roots, okay? So that means that they have the same roots to that polynomial, and therefore it means that they must have the same eigenvalues. So if you have two similar matrices, it actually means that they have the same eigenvalues and therefore the same multiplicities, okay? So each eigenvalue is going to have the same multiplicities, okay? So they have the same characteristic equation, which means they have the same eigenvalues and multiplicities. Okay. Let's prove this. This is in the notes if you want to follow along. So at the moment, you know that if A and B are similar, then there is some invertible matrix P such that that is the case. So what I'm now going to do is find what A minus lambda I is. Okay. Now A minus lambda I know that A is P inverse. And I know, I'm just going to rewrite this, I is the same thing as saying P times P inverse. You could also write it as P inverse P, but just so that I have what I need. I know that if I multiply a matrix by its inverse, I get the identity. So I've just rewritten this identity as P times P inverse, okay? I've done it that way around for a reason. Remember that matrix multiplication is not commutative, okay? So that's a good thing to remember when we go through this. What I'm now going to do is rewrite this thing. I'm going to pull that matrix P out the front. And I'm actually going to rewrite that like that, okay? This thing is exactly the same as this, because if I were to pull that lambda back out to the front here, I would get P times the identity times P inverse, okay? That is just P times P inverse. Okay, so the fact that I've put the identity in the middle makes no difference whatsoever, because any matrix times the identity is just itself. So all I've done is rewritten this to give me that. Now what you will see is that on both of these terms, I have my matrix P on the left and P inverse on the right. So I can rewrite this by factoring out P on the left and P inverse on the right. Now, when I take a determinant of A minus lambda I, that is the same thing as saying the determinant of this thing here. So that's the determinant of P times B minus lambda I, P inverse, okay? Determinant of a product is equal to the product of the determinants. So I can rewrite that as the determinant of P times the determinant of B minus lambda I times the determinant of P inverse. Okay. Each one of these is just a real number. The determinant of a matrix is just some real number. Therefore, I can move these around and I can say I'm going to bring that determinant of the B minus lambda I to the front and swap it with the determinant of P. They're just real numbers. You can commute real numbers. That's fine. Okay. Again, I'm going to go the other way this time. The determinant of a product is the product of the determinants. So the product of determinants is equal to the determinant of the product. I'm going to use that here. So I'm going to combine these again to get the determinant of a product. That's going to give me the determinant of B minus lambda I multiplied by the determinant of P times P inverse. This thing here is just the identity. The determinant of the identity, okay, it's just the determinant of technically actually a diagonal matrix, but you can think of it as upper or lower triangular. All we do is take the product of the terms on the diagonal. Well, the only terms on the diagonal are ones, so the determinant of the identity is just 1. So this thing, if this whole thing here is 1, that just gives me the determinant of B minus lambda I. And therefore they have the same characteristic equation, they have the same polynomial, hence the polynomial is going to have the same roots, hence they have the same eigenvalues with the same multiplicities. Okay, just be aware this does not work the other way around. Okay, just because two matrices have the same characteristic equation doesn't mean they're similar. Okay, so it only works in one direction. It doesn't necessarily work the other way around. And as I said, make sure you don't confuse this with row equivalence. Okay, one matrix that is row equivalent to another matrix can have completely different eigenvalues. Okay, if you think about it, any invertible matrix, okay, is row equivalent to the identity. Okay, if you've got an invertible matrix A, we know it can be reduced to the identity matrix. They are row equivalent to one another. Okay, the only eigenvalue of the identity matrix is lambda is equal to 1, and that has multiplicity n, because for I, let's say you've got an n by n identity. Okay, you're going to have 1s all the way down the diagonal, 0s above it and 0s below it. Okay, so that means it's an upper or lower triangular matrix, whichever way you want to look at it. It's actually diagonal. So lambda is equal to 1 is the only eigenvalue of I, but it has multiplicity n. Okay, it occurs n times. Okay, so lambda is equal to 1 has multiplicity n. But any invertible matrix A is row equivalent to I. But not all invertible matrices A have just the eigenvalue lambda is equal to 1 with multiplicity n. Okay, they can have whatever eigenvalues they like, it doesn't matter. Okay, but the thing that they are row equivalent to has only one eigenvalue with a multiplicity of n. So bear that in mind, that row equivalence actually has nothing to do with eigenvalues, okay, and with similarity of matrices. Okay, so keep that in mind when you do this and don't get them confused, because when one matrix that's row equivalent to another, by doing the row operations, you're actually changing the eigenvalues of a matrix. So please keep that in mind. Okay, the only other thing that I want to mention, there is a proof for this. This was actually in 5.1 right at the end, but I didn't get to it in the last video. We will use this in the next couple of chapters, so it is a good thing to keep in mind, this theorem. If you have a certain amount of eigenvectors, let's say R eigenvectors, with R distinct eigenvalues, okay, the eigenvectors that go with the distinct eigenvalues are actually linearly independent. Okay, so if V1 through VR are eigenvectors of a matrix A that are associated with the R distinct eigenvalues. So when we looked at this before, where we had the 4x4 matrix, it had 3 distinct eigenvalues. Okay, so the eigenvectors that would be associated with those 3 distinct eigenvalues, that's what I'm looking at here. So if you've got R eigenvectors that are associated with the R distinct eigenvalues of the n by n matrix A, we'll call them lambda 1 through lambda r. Then V1 through VR, so the eigenvectors that are associated with those R distinct eigenvalues, they are actually linearly independent. Okay, there is a proof for this. If you do want the proof for this, I'm not going to go through it, but you can read it. It's on page 272. It may be a good thing to just read through. It's going through a lot of the stuff that we've already talked about. Some of it's a little more in depth than what you need, but it's using exactly the same, like all the same formulas and all the same like construction of proofs that we've done before. So go ahead and look through that, but it is a good theorem to remember that the eigenvectors associated with the distinct eigenvalues are actually linearly independent from one another. Okay, that is it for 5.2. If you have any questions, please let me know and I will be more than happy to help you. And I will see you in the next video.